Page 7 of Math HL, Chapter 16, Eulers and Complex Numbers. So, recall from the investigation that when multiplying complex numbers, z equals modulus of z cis theta and w equals modulus w cis phi, that the magnitude, or the modulus of z times w is equal to magnitude of z times the magnitude of w, and the argument zw is equal to theta plus phi. Okay, so let's look at 1a. Write z equals 2 minus 2 pi in polar form. So I think the easiest way to do this is to draw a unit circle triangle. So we got 2 to the right and 2 down, because the real part is positive 2 and the imaginary part is negative 2. So that is 45 degrees down. So I would write that the length of the hypotenuse is 2 square root of 2. Because if this is 2 and this is negative 2, then the hypotenuse would be 2 square root of 2. So I got 2 square root of 2 times cis for negative 45 degrees, which is also negative pi over 4, right? B. Hence, multiply z by 1/3 cis pi over 3. Okay, so let's do that. So we got 2 square root of 2 cis negative pi over 4. We're going to multiply that by 1/3 cis pi over 3. So how we do that is we multiply the two modulus together. So that would be 2 square root of 2 divided by 3, that would be the new modulus of the resultant vector. And the cis thetas you combine by adding. So negative pi over 4 plus pi over 3, we would make a common denominator, which would be 12. So negative pi over 4 is the same thing as negative 3/12 pi. Positive pi over 3 is the same thing as 4/12 pi. So if you add those together, it's 1/12 pi, right? So cis pi over 12. So that's the answer for B. Next one, illustrate what has happened on an argand diagram. Okay, so first I'm going to draw 2 minus 2i on an argand diagram. So I'm going to draw that with a green. 2 minus 2 pi, it looks kind of like that. And then the next thing I'm going to do is I'm going to multiply it 1/3, I'm going to multiply it times 1/3 cis pi over 3. So that would look kind of like that. Okay, I'm going to multiply the purple and the green together. And what I'm going to get is something that is at the angle pi over 12, which is like 15 degrees. So it looks kind of like that. Its length is going to be 2/3 square root of 2, which is going to be not as long as the green one, right? Because the green one is 2 square root of 2. We're doing 2/3 square root of 2, so it's going to be like much shorter. So it would kind of look like that. Okay? Maybe it's even smaller than that. C, D. What transformations have taken place when multiplying z by 1/3 cis pi over 3? Okay, so basically we have done a rotation of, and when they say a transformation, like you look at the original vector, which would be the green vector. So when you multiplied it by the purple vector, what happened to the green vector? Okay, first of all, did it get shorter or longer? Well, obviously it got shorter, didn't it? And the reason why it got shorter is because the modulus of the purple vector is 1/3, it's less than 1. So actually what happened was the modulus of z, it was compressed by 1/3, right? Right? Maybe we could say stretched by 1/3, because if we say compressed by 1/3, it makes it, it's like, okay, compressed by 1/3, is that a stretch or is it? Okay, so it's stretched by 1/3. It actually became quite smaller, right? And the other thing that happened was it got rotated um, because we added pi over 3 to negative pi over 4, which was the original direction. So we rotated the vector um, counterclockwise by pi over 3. Okay, number 3. Use complex number methods to find in simplest surd form. Surd just means that you can leave the radicals in the answer. Like the square root of 3 and the square root of 2 that sometimes comes out of unit circle, don't find it decimal versions of the answer. So let's try to find what cosine pi over 12 and sine pi over 12 are based on what we know about complex numbers. So doesn't this previous problem where we took an original angle, which was pi over 4, and we rotated it by pi over 3 in order to get pi over 12, doesn't that kind of inspire you as far as like, hey, I can actually make a cis number for angles that are not special angles for the unit circle? I can like find cosine and sine for those by doing manipulations on complex vectors of pi over 3, pi over 4, the special angles. So let's try that. So basically, if we could find cis pi over 12 in surd form, then we're home free, right? So what if we took the two cis's that we can figure out pretty easily in surd form, which are cis pi over 3 and cis pi over 4, what if we combine these in some way so that we could make cis pi over 12? And remember that if you have cis pi over 3, if we have pi over 3 minus pi over 4, remember that gives us pi over 12, like in the last problem. So if we did something like, if we did cis pi over 3 divided by cis pi over 4, that would be equal to cis pi over 12, right? Because if we have cis pi over 3 divided by cis pi over 4, that is equal to cis pi over 3 minus pi over 4, which is equal to pi over 12, okay? So what if we tried to do this? What if we found cis pi over 3 and divided by cis pi over 4? So cis pi over 3 is a unit circle triangle that is about 60 degrees, okay? So, oops. So it looks kind of like this. And if you remember, if this side is 1, this side is 1/2, and this side is square root of 3 over 2. So this is the pi over 3 triangle. And so if I was going to write this in surd form, I would write 1/2 plus I square root of 3 divided by 2. Okay, and I would divide that by cis pi over 4. Cis pi over 4 looks kind of like this. It's got 1 here. It's got 1 over square root of 2 and 1 over square root of 2. So I could put 1 over square root of 2 plus I 1 over square root of 2. So I've got cis pi over 3 divided by cis pi over 4 in surd form. Do you remember how we could make this into one a plus bi type of number? We just need to multiply the denominator by the complex conjugate. So what if we try that? So we're going to multiply the bottom by 1 over square root of 2 minus I 1 over square root of 2, because that would be the complex conjugate. And we multiply both the top and the bottom by the complex conjugate. So we would get, I'm going to put this over here. Okay. So we would get the bottom would be 1/2 plus I or minus I squared, so that would be plus 1 half. And the inner and the outer terms, when you do FOIL, are going to cancel each other out because one of them is going to be plus I and the one is going to be minus I. So we just end up with a real, two real terms. And that's perfect because we wanted to get rid of the imaginary on the denominator. Now on the top, we can do FOIL also. So we get 1 over 2 square root of 2 for the first term. For the last term, we get minus I times I is going to be positive 1. Square root of 3 over 2 times 1 over square root of 2 is going to be square root of 3 times 2 square root of 2. And then the inner and the outer terms would be plus I. The inner term would be square root of 3 times square root of 3 on top and 2 square root of 2 on the bottom. And the outer product would be minus I, and it would be 1 half times 1 over square root of 2, which is 1 over 2 square root of 2. So the bottom is just going to be 1, which is perfect because we don't need to divide by anything anymore. The top, how convenient that all the denominators are 2 square root of 2, right? So the real parts, I'm going to combine them. I'll get 1 plus square root of 3 over 2 square root of 2 for the real part. The imaginary part, I'm going to have plus I times square root of 3 minus 1 over 2 square root of 2. That looks very symmetrical. If we arrange square root of 3 plus 1 here in the other order, it looks a lot like the imaginary component, doesn't it? It's just a different sign. The only thing we're going to do now is we're going to try to get the radicals out of the denominator because some people, math people, don't like that. If I multiply the bottom and the top by square root of 2, the bottom would become 4. The top would become square root of 6 plus square root of 2. The imaginary number would become 4 on the bottom and square root of 6 minus square root of 2 on top.